All right, so we're continuing with the ideal gas law, and we're looking at some of the common calculations that are associated with that ideal gas law. And the first of these is something that is pretty common to do, and that is to take a density. Well, the problem with gases is that gases tend to be pretty large in terms of their volume. And so it's not always easy for us to calculate to measure the density of a gas unless we have some way of determining its mass or its temperature and pressure from the ideal gas law. And so when we talk about densities of gases, again, we're thinking grams per liter here. Grams can come from measurement of mass. Volume can come from the ideal gas law. And one of the most common applications of this is our idea of buoyancy, in particular of gas buoyancy. Because when we talk about gases, while we do say that gases will uniformly mix with each other, one important thing to note is that gases, based upon their mass, do have a tendency to kind of congregate in certain areas of a container as opposed to being truly and fully random in their motion. So if I have a mixture of gases, what I'll notice is that lighter gases will have a tendency to kind of gravitate and float on these heavier gases. Now, we see this anytime we have a helium balloon. If you have a balloon filled with helium or filled with hydrogen, its natural tendency, its natural density is considerably less than that of nitrogen, which makes up the majority of our air, which is why when you hold a balloon and then release it, the first thing that'll happen is that the balloon will start to go up to the upper ends of the room. Now, one other application of this that is important is we can also base density on ideas of temperature. Again, think about our Charles law. If pressure is held relatively constant because we're in an open atmosphere, the temperature and the volume are going to vary directly with each other. And since volume and temperature are directly related, if I increase the temperature of the gas, that'll cause the volume of the gas to expand. And if I have a trapped gas, as in the case of a hot air balloon, that expansion of the gas is going to make the gas inside the balloon less dense than the gases outside the balloon, and that's going to cause the balloon to rise. And so we see this often in these kinds of circumstances here. This is largely how a hot air balloon works. Now, depending upon the scenario and how things go, you can get a balloon to rise by heating the air inside of the balloon, and the balloon will expand and will rise up as a result. If you want the balloon to go down, there's usually a vent here in the top of the balloon that'll allow you to let some of that air out, which will decrease the volume, and we come back down to our normal mass, our normal density. We start to descend. So let's take a look at an example here. I have a reaction occurring between nitric acid and sodium bicarbonate. They mix together, a reaction takes place where gas is one of the products. The gas has a density of 1.83 grams per liter at 1 atmosphere of pressure, 23 degrees Celsius. What we want to know is what is the molar mass and the identity of the gas. Well, if we do the chemical equation, we can probably get a pretty good idea of both of these questions. Nitric acid reacts with sodium bicarbonate to make sodium nitrate. and carbonic acid, H2CO3. Now, the thing with carbonic acid is that it rarely exists in this pure form here, and often, in fact, pretty much every time we see it as a product of a reaction, we have to understand that it will undergo a decomposition, and that decomposition will yield water and carbon dioxide. So carbonic acid is kind of the fancy way of saying that we have carbon dioxide dissolved in water. And since the two are not terribly soluble in each other, and think about the soda exercise that I did yesterday, as soon as we crack open that pressure and bring the pressure inside the can up to atmospheric pressure, the carbon dioxide bubbles up and starts to get the heck out of that soda. So very often carbon dioxide is going to be the product of this reaction. So if we were just to base it off of the reaction itself, we would be able to say pretty definitively that it's going to be carbon dioxide that we're talking about. But let's go ahead and use the other data here to help us out. With the density of 1.83 grams per liter, what we are saying is that 1.83 grams of our substance is equal to 1 liter of our substance. And so to that end, if we want to figure out the molar mass, remember molar mass is equal to mass of substance in grams divided by moles of substance. And so I already have a mass of substance. What I need to figure out is the number of moles of substance. And this is where the ideal gas law will ultimately help us. PV is equal to nRT. My pressure is 1 atmosphere. My volume is 1 liter. I don't know what N is. My R value is going to be 0.08206 liter atmospheres per mole Kelvin. And my temperature, 23 Celsius, is 296 Kelvin. So solving for N, the number of moles, I get 1 times 1 divided by 0.08206 divided by 296. I get 0.0412 moles of my substance. So for molar mass, I got grams of substance, 1.83 grams divided by moles of substance, 0.0412 moles. And the three significant figures, 1.83 divided by 0.0412, I get 44.4 grams per mole. Now, of these options, this is the only the carbon dioxide would make sense here. Carbon dioxide's molar mass is 44.0. So we're within rounding error, certainly here. We're only different on the last significant digit. And if we compare that to water, which has a mass of 18, or sodium nitrate, which has a mass of 85, this is certainly the best option. All right, any questions about this example?
No.
All right. So probably the most popular and most common direction that we can go with these data is doing something called gas phase stoichiometry. Now, in gas phase stoichiometry, what we are doing is we're applying those same stoichiometric principles that we saw in Chapter 7, Chapter 8, and now we're bringing them here to talk about gases. And the way that we can do it is by using our ideal gas law. We now have a way of interconverting between the volume of a gas, which is usually pretty easy to measure, and the number of moles of gas, which is not often as easy to measure and would allow us to plug into our mole map. So we've already seen circumstances where we have added to this already. We added a box on each side not that long ago for milliliters or liters of solution. And the way that we tied it up to our stoichiometry was with molarity. Now we can add another set of boxes and pretty much talk about the same kind of thing. Milliliters or liters of gas. Milliliters or liters of gas. And the thing that ties these together is the ideal gas law. And so from this perspective, we now have multiple ways, and the whole key for stoichiometry is getting whatever it is that we are measuring into moles. If I can get it into moles, I can use the moles of that substance and a balanced chemical equation to turn this measurement into pretty much any other measurement if I have that balanced chemical equation. So let's put that into action. Automobile airbags inflate during a crash by the rapid generation of nitrogen caused by the decomposition of sodium azide. Question is, how many grams of sodium azide are needed to produce enough nitrogen to fill a 48 by 48 by 25 centimeter bag to a pressure of 1.2 atmospheres at 15 degrees Celsius? So if we go to our map here, what we are trying to do is we are trying to use the volume of a gas to figure out the number of grams of a reactant And so to do that, we're going to convert following the lines here. By using the ideal gas law to get us to moles of the gas, balanced chemical equation to get us to moles of the sodium azide, molar mass of sodium azide to get to the grams. And so if we have this here, we've got a pressure, 1.20 atmospheres. We've got a temperature, we just need to convert it into Kelvin. And if we do this multiplication, that would give us a volume of the bag in centimeters cubed. So if I do that, 48 by 48 by 25, I get 57,600 cubic centimeters. Now, Brett, since you're the only one here, I'm going to have to ask this question to you. To use the mole map, I need milliliters or liters. How can I turn those cubic centimeters into either one of those units?
You can just convert that to meters. Cubic meters.
You could. That's probably a little bit more of a complicated conversion, just because you got to do that 100 cubed business. The easier thing to do, I would think, is if you recognize that milliliters and cubic centimeters are the same thing, then what that really means is that this is 57,600 milliliters, which would be 57.6 liters. That's probably the easier way out, just because even if I convert this to cubic meters, the value of R that I need to use would have to rely on me converting this atmospheres into kilopascals in order to use the value of R with cubic meters in it. So I've managed to convert the volume here into a liter volume by taking advantage of this definition between milliliters and cubic centimeters. So now I need to use the ideal gas law. The number of moles of gas is equal to PV over RT. So we've got a 57.6 liter bag times 1.20 atmospheres divided by 0.08 206 liter atmospheres per mole Kelvin, and 15 degrees Celsius is 288 Kelvin. So quick check of my units. My liters cancel, my atmospheres cancel, my Kelvin cancel. I'm left with 1 over moles, which would be just moles. (57.6) times 1.2 divided by 0.08206 divided by 288. To 3 significant figures, I get 2.92 moles of nitrogen. Now the last part of this here is just normal stoichiometry. I'm going to take my balanced equation, 3 moles of nitrogen for every 2 moles of sodium azide. So my moles of nitrogen cancel. And then the last step here is we want grams. So 1 mole of sodium azide and sodium is 22.99, nitrogen is 14.01, and there are 3 of them. 65.02 is the molar mass. So 65.02 grams of sodium azide is equivalent to the 1 mole. And so 2.92 divided by 2, or multiplied by 2, multiplied by 65.02, divided by 3, it would take to 3 significant figures 127 grams of sodium azide to do this. And so that's a pretty significant amount of that compound. But if we were trying to blow up an airbag that was that large, 57.6 liters is pretty large. I would imagine that is probably one of those side curtain airbags and not the one that comes out of the steering wheel. But at that particular volume and particular pressure and temperature, that's what it would take. All right, question on that one?
Nope.
All right, we don't have a group here, so you and I can just discuss this. What if I have a cylinder that has nitrogen and oxygen gases on the inside? How can I determine the total pressure? How can I determine the individual pressures? So let's start with the first one. What is a way that we could determine the total pressure of gas inside of the cylinder?
Wouldn't you just use like the combined gas law? It would just be pressure, volume over temperature.
Okay. If we knew those other parameters, sure. But really, the answer to this question is even easier than that. We just measure it.
Oh, okay.
You take a pressure gauge and you put it up to the cylinder, it would tell you what the pressure inside the cylinder was. You do that all the time. If you ever check the pressure in your car tires, inside your tires, it's air. It's a combination of gases. And yet when you take that tire gauge and you take the pressure of the tire, it tells you the pressure inside of the tire. So when I have a mixture of gases, determining the total pressure is easy. I just measure it, using some kind of a pressure gauge or a pressure sensor or something along those lines. But when it comes to measuring the individual pressures of the components, take that tire gauge example again. how do I measure how much nitrogen is in the tire, how much pressure the nitrogen is giving versus oxygen versus carbon dioxide versus anything else? That answer is not nearly as simple. It requires a little bit more know-how on our part. Now, to that end, we've talked about this to a certain degree already. When we talked about Raoult's law for multiple volatile solutions, we mentioned this idea previously, the Dalton's law of partial pressures, which says that the overall pressure of a cylinder or of any gas sample is equal to the sum of the individual pressures inside of the cylinder. What we didn't talk about at the time, because it wasn't terribly relevant to us at the time, is that the individual pressure of any of one of these components is equal to the mole fraction of that component multiplied by the total pressure of the gases. Now, this is different than Raoult's law. Raoult's law was concerned with vapor pressure, and so this equation probably looks familiar, but it's not quite the same. The difference here is that instead of total pressure in this position, we would talk about the true vapor pressure of the liquid, as opposed to just the total pressure of the gases. Now, this does have some utility for us in certain kinds of chemical reactions. And so anytime we do a chemical reaction where we are collecting gas over water, this is a common kind of attribute. And so one of the most common reactions that is done in this manner is the decomposition of chlorates. And so if we have a potassium chlorate, for example, and we heat it up, the end result is that the potassium chlorate will decompose into potassium chloride and oxygen gas. And this is a picture of that reaction taking place. And so what happens, the reaction here, the decomposition happens in the test tube. The oxygen gas slowly starts to make its way up to the top of the test tube, where there is a glass tube that goes down into a bucket of water, and we measure the amount of oxygen that goes in by how much water it displaces. So we can measure the volume of this jar beforehand, and assuming that we fill it up with oxygen, we know that that same amount of volume is now occupied by oxygen. Problem is, in this space also, because we are collecting over water, we're going to see some water vapor in this airspace as well. We know that water, regardless of temperature, is going to evaporate, at least somewhat. And so when it comes to measuring the total pressure, which in a case like this, since the reaction is being done in an open atmosphere condition, we know that the total pressure, which would be the atmospheric pressure, is equal to the pressure of the oxygen plus the pressure of the water vapor. And so to that end, we can solve certain kinds of problems. So this is a very common lab experiment. If we were doing an on-campus lab, we would be doing this experiment. There's no real safe way to do it outside of a lab, though, so we're going to have to kind of stick with hypotheticals here. So let's look at number 7. 25 degrees Celsius, we have a 1 liter flask that contains 0.03 moles of oxygen, 150 milligrams of nitrogen, and 2.6 times 10 to the 21st molecules of carbon dioxide. What we want to do is calculate the partial pressure and the mole fraction of each gas. Now, it sounds like there's a lot of work in there, and in fact, there is. But there are a number of ways that we can come about and do this reaction and this as well. So you're going to need a little bit more space than this requires. So I'm going to throw it over to the whiteboard here. And we have a 1.0 liter flask at 25 degrees Celsius. And in that flask, we have 0.030 moles of nitrogen, 150.0 milligrams of, we have 0.03 moles of oxygen. We have 150 milligrams of nitrogen. And we have 2.6 times 10 to the 21st molecules of carbon dioxide. What we want to know is partial pressure and mole fraction of each. Now, figuring out the mole fraction of each is not that difficult. After all we need to do is figure out the number of moles of each of these, and then do mole fractions for them using our mole fraction equation. Not too terribly difficult or stressful there. In fact, we could start with our 150 milligrams of nitrogen and converting that into moles. (1,000 milligrams in 1 gram), 28.02 grams of nitrogen in 1 mole of nitrogen. And so 150 divided by 1,000 divided by 28.02, I get 0.005353 moles of nitrogen. In a similar kind of way, I can take that number of molecules of carbon dioxide and convert it to moles of carbon dioxide. Here I just need Avogadro's number. Avogadro's number of molecules is equal to 1 mole. And so 2.6 times 10 to the 21st divided by 6.022 times 10 to the 23rd, we get 0.0043 moles of carbon dioxide. And so the total moles of gas would be equal to 0.03 So 0.03 moles of oxygen plus 0.00535 moles of nitrogen plus 0.0043 moles of carbon dioxide. We would get 0.040 moles total. And the significant figures get a little bit sticky here. The number that actually comes out of the calculator is 0.03965. Remember, for adding, we always have to round to the leftmost estimated digit. So we have 3 decimal places here, 5 here, and 4 here, which means each of these 3 digits was estimated. So we round to the leftmost estimated, which means our final answer has 3 decimal places as well. So we've done the first step. We've figured out the total number of moles. To figure out the mole fractions, we would need to use our mole fraction formula. Mole fraction of oxygen is equal to the moles of oxygen, 0.030, divided by the moles total, 0.040, .03 divided by 0.04 would be 0.75 as the mole fraction. For the mole fraction of nitrogen, I would have 0.005353 divided by 0.040 0.005353 divided by 0.04 to 2 significant figures, I would get 0.13. For carbon dioxide, I would take the 0.0043 and divide by 0.040. And if I do that, I get 0.11. Now, you may be saying to yourself, well, hold on, wait a second. These 3 don't add up to 100%. They add up to 0.99. That's not terribly uncommon when we have a lot of rounding to deal with. And especially considering how much we rounded off this 0.04 on the bottom, it would be just as acceptable to use that subtraction concept and end up with a value of 0.12 here for carbon dioxide, because we said that it was going to be equal to 1 minus the 0.75 of the oxygen and the 0.13 of the nitrogen. That's okay. So in these kinds of problems, it's not uncommon to see little bits like that where things don't quite fully add up because of all the rounding, and that's okay. So we've got the mole fractions. We've done that part. How do we deal with the partial pressures? Well, for the partial pressure, remember that the pressure of any component is equal to the mole fraction of that component multiplied by the total pressure. So I need the total pressure. Now, obviously, if I could, the total pressure would be the thing that I would look at by just measuring it if possible. I can't do that here because it's not given to me. But what I can do is I can take advantage of the fact that I have a certain number of moles of gas at a certain volume and a certain temperature. And if I have any three of the four parameters, I can use the ideal gas law to solve for the other. So the total pressure is going to be equal to nRT over V. Total number of moles is 0.040. For R, let's use 62.36 this time. For temperature, 25 degrees Celsius is 298 Kelvin. And for the volume, I had 1.0 liter flask. So I do those calculations. 0.04 times 62.36 times 298 divided by 1. I get 740 millimeters of mercury as my total pressure. And so now that I know the total pressure of the system, I can apply each of these mole fractions to it to figure out their partial pressures. So the partial pressure of oxygen is equal to 0.75 multiplied by 740 millimeters of mercury, which would be, all right, 560 millimeters of mercury. The partial pressure of the nitrogen would be equal to 0.13 multiplied by 740. Point 0.13 multiplied 740 is 96 millimeters of mercury. And then finally, the carbon dioxide would be 0.12 times 740, which would be 89 millimeters of mercury. And again, because of the rounding, if I take 560 plus 96 plus 89, I get 745. I get a few extra millimeters of mercury. And again, you're going to have that because of the rounding, because we don't have many significant figures here at our disposal. And that's just something we have to deal with. Right. Pretty long example. Do you have any questions?
No, do not.
Okay. So all right, let's look at another example then. This one's a lot simpler. Let's say that we have a sample of potassium chlorate that we heat and decompose to produce oxygen gas. Total volume of the collected gas is 329 milliliters. Pressure is 744 torr. The question is, how many moles of oxygen are formed? Well, the missing piece of information that we would need here is that the vapor pressure of water at this temperature is 23.8 torr. And we could get that from any reference table at 25 degrees Celsius. So the real kick here is we know that the temperature and the volume are going to be the same for the oxygen as they are for the mixture. The pressure is what is ultimately going to change. And so we need to use Dalton's law here to say that the pressure of oxygen is equal to the pressure in total minus the pressure of the water. And so knowing that 744 torr was our total pressure, 23.8 torr is our vapor pressure of water, the pressure of the oxygen would be 720 torr. Now that we know that, now that we have that information, once again, we're presented with, I have a pressure, a volume, and a temperature. 3 of the 4 parameters are known, so the ideal gas law can help me to figure out the one that I'm looking for, and that's the number of moles. PV is equal to nRT. My pressure is 720 torr. My volume is 0.329 liters. I don't know N. R in this case would be 62.36 liter atmospheres per mole Kelvin. And my temperature at 25 Celsius is 298 Kelvin. Solving for N, 720 multiplied by 0.329 divided by 62.36 divided by 298. I get 0.01127 moles of oxygen. Now, it should be noted that the last problem that we did, the one on the whiteboard, we could have solved this way, just as a point of principle. Like I said, there are many ways to solve that problem. We could have plugged in the individual numbers of moles into the ideal gas law, and combined with the temperature and volume, figured out the pressure of each one, and then combined them to find the total pressure, and found the mole fraction, in either way. That would have been acceptable as well. But the important thing to kind of draw out of this is that the ideal gas law can be applied for individual components of a mixture or for the total mixture, depending upon what the conditions are. And so what we have to understand is that pressure, volume, and temperature, or at least volume and temperature, should not change if we are looking at a mixture of gases. Because if I'm looking at a mixture of gases, the container that they're in and the temperature at which they are being held should be the same for all of them, and would be the same for the mixture as a whole. So the things that are in play there are the pressure and the number of moles, and that's the interplay that we're looking at in this scenario. Questions on this one?
Where did the 23.8 torque come from for
This
this
would
problem?
just be, this is the vapor pressure of water at 25 degrees Celsius.
Oh, okay.
This would just be found in a reference table of some kind.
Oh, okay, I got you.
Yeah, there's no real trick to it. This is a reference value. There are a number of different reference books out there that would have this kind of information in it.
Okay.
All right, anything else?
No.
Okay, to this point, we have largely been talking about ideal gases. That is, gases that behave strictly according to the kinetic molecular theory. But there were some assumptions that we've made along the way. One of the assumptions that we made along the way is that gases don't have any volume. The molecules don't. The gas molecules don't become attracted to each other. And what we'll see is that when we're at higher pressure and lower temperature values, those ideas are not necessarily true. So if I decrease the volume and thereby increase the pressure, the more I decrease the volume, the more significant those molecular sizes are actually going to be. And when I'm at low temperature, I have to understand that at low temperature, those attractive forces are going to become more important, because since the molecules aren't moving as fast, when they collide with each other, the chances of them interacting with each other as they collide and attracting each other as they collide, as they come close to each other, is significantly greater. And so where this attacks the kinetic molecular theory are in the first and then the fifth postulates, those assumptions that we made. Now, the good news for us is that the majority of the work that we do with gases is going to fall into ideal behavior. Only in very special circumstances would real behavior have to be applied. But luckily for us, we can account for this behavior in the following way. And the way that we do it is using something called the van der Waals equation. Now, the van der Waals equation applies corrections to the ideal gas law based upon attractive forces that exist between molecules and the size of the molecules themselves. And so where that gets applied is here. And so this first correction is the correction for attractive forces that exist. The second correction here is the correction for the volume. And so in those special circumstances, we can use the van der Waals equation, and the values of A and B are specific to a substance. So if I'm looking at oxygen gas, oxygen is going to have its own values of A and B. Carbon dioxide is going to have its own values of A and B, and so on. And so Depending upon how big the molecule is, you're going to get different corrected factors in there as well, depending upon the polarity, the intermolecular forces that exist. You're going to get different attractive forces, different effects there as well.
Now this is only for when it's not in an ideal gas situation. So basically, like a more compressed situation or something like that.
Yeah, so
Okay.
we would see these primarily if we have gases under extremely high pressure or extremely low temperatures, or both.
Okay.
So where we would see this in things like cryogenic materials, or even just gases that are under extremely high pressure. If pressure is of concern, then that is something that we would have to worry about, and something that we would have to account for. But otherwise, the ideal gas law dominates the majority of the things that we would be doing, as far as any kind of calculations would be concerned.
Now is there like an ideal pressure where they kind of start taking into consideration for this one versus the other formula?
So I kind of glossed over this.
Oh, okay, I get you. So they got a chart.
So we really don't seem to see too many deviations. If they zoom in on this area, so this covers us to like 10, 15, 20 atmospheres of pressure. We don't see significant deviations on one side until we start to hit, 100 atmospheres or so. And then the deviations on volume of gas molecules really start to take aim in the 400 to 800 atmosphere range. So unless you're working, like I said, at really high pressures, this is kind of a non-starter.
Okay.
Because yeah, there's, I think in your textbook they zoom in on this window here and they show that for the first 25 atmospheres of pressure or so, all of these gases are really pretty close to that ideal gas line, with very few or minimal deviations. It's really when we get to these higher, more extreme kinds of situations. And so, I mean, you think about where you work with gases the most often, like a compressed gas cylinder. Compressed gas cylinders usually work in the 3,500 psi range. 3,500 psi would be about 240 atmospheres. So if we were doing reactions inside of those gas cylinders, then yes, we would probably have to make some considerations for that. However, most of the time when we work with gas cylinders, it's just they're a storage tank. Their storage is going to, have very little impact on their reactivity. They only come out to play when we let them out of the tank. And when we let them out of the tank, they go from 3,500 psi to 15 psi, which is about atmospheric pressure. And so as soon as they get let out of the tank and come out to normal conditions, they're behaving ideally again. Now, if we were evaluating carbon dioxide in a compressed gas cylinder, let's say that, okay, we know its pressure, we know its volume, we know its temperature, how many moles are in there, then yes, the van der Waals equation would have to be used to account for the compacting that would be taking place inside of the cylinder itself. So if I wanted to figure out N, how many moles of carbon dioxide are in this cylinder, I would have to use these corrections to take into consideration those the high pressure situation that they're under. But aside from that, I mean, there aren't a whole lot of applications unless you're doing some really specific kinds of pressure work. All right, you got any other questions?
Nope, not at the moment.